Thank you very much, David. Thank you for the very kind introduction. It's a privilege and an honor for me to give this lecture at Imperial College. I assume that I am there. Unfortunately, I'm not. And so let me thank you, Azada Ayub, who really triggered this idea for me to come to England. And of course, the Imperial friends who made the visit in Pisa, because this was born after 2 visits by the Imperial friends in Pisa, Virgo. So Rod Jones and Rita Leak were really pushing for doing this. So I'm very glad to be here, and I'll present what we are doing. I'm very glad that we were given the opportunity to present this. So the work is by 2 collaborations, a huge number of people that we'll see, and it's about the 3 detectors that you see an aerial view here in the front page, which are the LIGO detectors in Louisiana and Washington, and the Vigo detector in Kashina. So we have to introduce.
Francesco, can you yes. speak up a bit? People are saying you're very soft.
Oh, I see. Okay, I will. So the
thank you.
So let me begin. Let me say what we are talking about when we talk about gravitational waves. It's a complex subject. It took a lot of time to very bright people to sort this out, and it took 100 years to detect them. So it's by no means a simple thing. But we start, hopefully. So what I will talk is a little bit about gravitation, geometry, and general relativity, about how you detect gravitational waves, what we've seen, and what is the perspective. So general relativity is something that starts with Galileo. Galileo was mentioned in the introduction, and Galileo discussed free fall of different bodies. And he said that bodies of different weight, in particular, take the same time to reach ground. And this was then published. He published this cautiously in the Netherlands rather than in Italy in 1638. So what can be seen is that the motion of a body by the force of gravity alone does not
Francesco,
depend.
Can you increase volume?
I will, yes.
Speaking louder has helped greatly for me, but people are still having some...
Okay, you might have this small background, but I hope it will not annoy too much. Is that better?
Need more.
Need more. Fine. Voila. Is this better?
That's better.
Okay. So we have that the motion of a body by the force of gravity alone does not depend on mass and not on weight, and all bodies that are not too far one from the other undergo the same acceleration. So what they have in common is the space that surrounds them, and as well as counting time. And so the idea is to move this to gravitation as a property of space-time. And what we can say is that in absence of gravity, light travels along a straight line as a constant speed. And in fact, if you think of it, we are using it to make our surveys, to locate bodies, and in fact to attribute a time here to events. So we can say that light weaves the fabric of space-time. And there's a famous architect who says that where there is light, there is space. And so where there is no light, there is no space. And so we can say that where there is light, there is space and time. And of course, when there is no light, you don't have the property. So light is going to define the properties of space-time. In presence of gravity, we have that light bends, time slows down, and geometry changes. So this is a famous picture of a famous experiment. Was done by Lord Eddington, I think, in 1919, and observing that light that passes close to the sun is deviated from what we would call a straight line trajectory. So this means that the geometry of space and time has changed because of the masses. Near the sun, the effect is of a few parts per million. On Earth is even less. So your real estate agent will not be able to use general relativity and the geometry to fake you on the surface of your flat. Now, masses, so generate curvature. We have this picture here, but this will not happen instantaneously. Gravitational waves are going to carry the information of curvature away from the masses that have moved, or cannot appear, but they will move somewhere, and they will tell about what the masses are doing, how the masses are moving. So we can say that these gravitational waves are ripples in space-time that propagate at the speed of light. The nice thing is that the waveform is preserved, energy is carried away, and so gravitational waves unveil the motion of cosmic bodies even when we don't see them, simply because of their mass, they're going to show up as with gravity. So these are the signals that are transmitted by space-time. On the left, we have a numerical simulation of what would appear, what would be space-time around the two orbiting black holes emitting gravitational waves. To do this, to detect gravitational waves, we need a very refined technique, which is called interferometry. And I'm going to spend a little bit of time on this. What is the effect that we need to observe? So we have these masses. We must assume that they are free. They should feel only gravity will be correct for what happens locally. And these free masses should move according to space-time curvature. Pick up a pointer. Okay. And so we can say that they are in free fall. And if a gravitational wave modifies the curvature when it's passing, then the light propagation, the masses will change their motion, light propagation will change, and the net result is that the distance between two masses at rest, that we observe to be at rest, is going to change. And this is an effect that increases with the distance. The farther the mass is, the larger the effect, and that's why we need the kilometer-sized detectors. But even over kilometers, the effect is 1 over 1 plus 20 zeros behind, 1 over 10 to the 20th. So it is very small. It is 1/10 of a billionth of the atomic radius, and this has to be measured about objects that are object of the size of everyday life. So we measured it on massive macroscopic objects. And in this case, these are glass cylinders with mirrors with a diameter of 35 centimeters and a mass of 42 kilograms. So this is a very, very tiny effect. It's really unimaginable. And people really thought that people doing this job were crazy. Here we have a representation, a picture of how the detection happens. And we see a beam that gets split by a semi-transparent mirror, beam splitter, goes at to an end mirror and comes back. And you see that the beam carries the information of the phase. And when going back, here we are in a situation in which the two phases, the two waves, light wave, are in counter phase. If the mirror moves, then the relationship of the phases is going to change, and there is going to be light that will be seen here. So this is a very clever principle of detection, which is extremely precise. It allows to make a comparison between distances, which somewhat takes away the fluctuation of the light source, and can be indeed sufficiently precise to perform the detection. So what we need is two arms that are perpendicular. We need a light source, and we need a long path for the light to travel. So this is this is a Michelson interferometer, and this is reality. The friends of Imperial came here and visited these buildings, and were here. This is the countryside. We have Pisa in the at the far end, and we have some fields that can make some noise and give us problems indeed. So this is advanced Virgo, which is running now. It is an upgrade of the Virgo interferometer, which is an adventure that started formally in 1994. It was by France and Italy. Then the Netherlands joined, Poland, Hungary, Spain. So it's truly a European international venture. And Advanced Vigo made the first observation run in 2017 in August. And it is a component of the global detector network I showed to the other two interferometers at the beginning. Then we had a second observation run that lasted almost 1 year. It was interrupted, as many things, by COVID. I should mention who are the people that are working. So let me start by the large LIGO scientific collaboration. They have built the interferometers that are in Washington State and in Louisiana. And it's a collaboration of more than 1,000 people. And you see that it spans all over the world. Just Africa is missing, but someday I'm sure it will come. There are 18 countries, and to this collaboration, there is a special contribution which is called globally the GEO collaboration, and which is made by UK and Germany. So out of this list, we should add with a privileged position, UK and Germany, who built an interferometer of 600 meters, GEO 600, which sits in Hanover. This is the UK contingent. So we have several collaboration, several institutions all over UK, as you can see. And I should mention that also in Imperial there is some. There is activity going on in this field, theoretical, that is extremely important. So the principle of detection was outlined. It gets implemented in something. This is still a schematic diagram, by having a powerful laser that should be very stable by itself. Otherwise, you measure the fluctuation in the wavelength rather than gravitational waves. You need to clean the light that comes in, and then the light gets split here in the beam splitter. And here there is a trick. There is a very clever procedure, which is called a device, which is called the Fidecaro cavity, which is able to multiply, in our case, by 100 the length of this cavity. So we are living, in fact, with an effective length of about 300 kilometers for each cavity. And this is done by having multiple reflections and multiple reflections with a semi-reflective mirror, which is placed here. These mirrors must be very well isolated from ground vibration. Ground vibration would kill by orders of magnitude the effect. And so there has been a device has been developed, which is simply, quote unquote, a chain of pendula, which is able to attenuate the vibration of the ground, which is transmitted here, and it's so that the mirror, which is here, will not feel the vibrations of the ground. There is always a little microseism. Under your feet, in 1 second, the ground moves by 1 micron, and so it's orders of magnitude above what you want for your detection. Everything has to stay under ultra high vacuum. And so this is the schematic. And we characterize our detector by presenting a noise curve. So this is a little bit complicated. I'll try to be, I hope to be able to explain it. We take a range of frequency. Waves are oscillating. The waves we are interested in are essentially audio waves, 10 hertz up to 10 kilohertz. So it's something that can be heard. And for each beam of 1 hertz, you count how much the system, the detector, gives a signal, how high the signal is in absence of gravitational waves. And this is by definition is noise. And the noise, total noise, is expected to be this black curve. To get there, you must reduce a number of noise sources that I would like to illustrate. So the first one was mentioned. It is seismic attenuation. Fortunately, the noise given by this seismic attenuation stays outside this graph. It stays on the left, and so we don't need to plot it. But this has required 15 years of work to obtain this result. Then we have here, this is the local gravity fluctuation. Whatever moves nearby the mirrors is bound to attract the mirror and is going to move it, and so fake a gravitational wave. And the computed rate of noise for this is given by the green curve. Let me mention here the scale. The scale is given in 10 to the minus 24 in strain. If you multiply by 3 kilometers, you get the displacement in meter that you would expect. And it's over 1 over square root hertz, because this is the way you mention noise here. This is an unavoidable effect. The only way to avoid it is to go underground or to go in space. We'll say something about it at the end. So here is going to be, there is going to be a wall for our detectors. Then there is what is called thermal noise. It's something that comes from the fact that your mirrors and the mirrors, they are suspended, they are at room temperature. And so there is some thermal motion. Thermal motion gets transmitted to the mirror through the dissipation that occurs in the suspending wires. And by using very thin fiberglass wires, 200 micron diameter, that will support the 40 kilogram mirrors, we are able to push this noise, which would be otherwise much higher, to the blue line that you can see. Then you are using light to make a measurement. Light is quantized. You are counting photons. It's a little bit more intricate than that, but counting photons gives the idea. And you have what is called shot noise. And this can be, you can go around shot noise with very clever ideas that come really from the quantum nature of light. And but still, the noise from the quantum nature of light is going to give the limit that you are shown here. What happens is that you are able, on one side, to reduce the error measurement on the phase, on real interferometry. On the other side, if you're clever, you can reduce the error due to the fluctuation in the number of photons, that is radiation pressure. Finally, the last thing is, this is really tantalizing. We have a big zone that doesn't allow you to profit from being clever with quantum light, and it is thermal noise dissipation on the mirror themselves. And the mirror, the substrate, is fused silica, is a beautiful crystal light resonating like a bell in a beautiful way. But we need to cover this crystal with thin coatings, because we want to make a mirror. We don't want only a glass, we want a mirror. And these coatings that get deposited with 6 micron over 20 centimeter, this is the cause of this noise that is present. And this is a serious limitation, because here there is a factor of 3. You could gain a factor of if you want to gain the same thing by increasing the length of the arms, you would go from 3 kilometers to 10 kilometers. So it's better to work on this, but also this is extremely difficult. Let me say that a lot of work has been done in various places, but in particular at the University of Glasgow, there is a very strong group that is working on these problems. Nevertheless, we are living with this, and we can do something out of it. Here are a few photographs just to show you what things look like. This is at the central building where the two beams intersect, and here we are at a lucky time where these super attenuators that you can guess are here are out of vacuum. The vacuum cap has been taken out, and the vacuum cylinders, because there is work that needs to be done for the upgrade. So this is a very special photograph. If you come, usually you see a closed cylinder and you don't know what is inside. This is one of the mirror. This is the beam split mirror, and it is freshly suspended to be used for the run. Cleanliness is something that must be respected, and so people have to work in somewhat difficult conditions, and having no dust going out. So let me go through a few things that have been done. So you probably you have heard of this first event that was detected, but let me use it to illustrate what is going on. So these are the signals that were recorded in Livingston, in Louisiana, and in Hanford. They are essentially raw signals. Some filtering has been made in frequency, but not much more. And you see that the two signals, they are the same, but at 3 kilometers apart. We made all possible checks to be sure that very unlikely coincidence would have the signals come out of the noise, and it was shown that this would require tens of thousands of years for this to occur. So it was decided, it was the indication that this is a true signal, something that is common to the two detectors. What does this signal mean? These are two massive objects that are orbiting one around the other. And we are seeing the last orbits of a binary black hole system. So the objects, not only we are seeing gravitational waves, but we are seeing really black holes at the very end of their life in this system. So these are the last orbits about the arrow. Then there is a merge phase in which the two black holes are so near that they are going to swallow one the other. And finally, what will result is still a black hole that is not yet perfectly circular. It has to ring down to release some energy and to become a black hole that has a mass which is the sum of the masses of two black holes minus the energy that was emitted, which in this case amounted to 3 solar masses in energy. And then this black hole will stay quiet probably until the end of the universe, because there is nobody will be able to see it again unless it meets a companion and builds another binary system. But this is a different story. This was on this slide. I reported the front page of the paper that was published. Was published the 12th of February in 2016. And in fact, this paper and the work done earned the Nobel Prize in 2017 to Ray Weiss, Barry Barsh, and Kip Thorne. And here you can see on the cover page of Physical Review Letters what we mean. There is an in-spiral, then there is the spiral gets tight, and then the two black holes merge and then form a single black hole. Then we had another run in which Virgo was able to participate. For some reasons, we could not take part in fact, our program of construction had 1 year delay with respect to LIGO, but we could participate in the second run. And in the second run, there is something really extraordinary that happened. Also, this perhaps you heard of it, but I would like to tell you about it. And it happened on the 17th of August of 2017. And this so here we have, there is a satellite, Fermi, who is meant to detect gamma ray burst, and then we have the interferometers on ground. And look what happens. I apologize, but of course we said that we should share the sound of the screen, but it's done. Okay. My apologies. So you will hear the sound of the gravitational wave in a sense, and also something different. So what you heard, it's a little bit translated because the frequency is not the same. But here you can see the graph. You see the very last moment of this signal. This is a time frequency graph in which you see that the frequency, there is a well-defined frequency that is seen by the detectors. This frequency increases. It makes what was called the chirp. And this is the very end, the merge of these two objects. And 1.7 seconds later, you've seen that there is a signal in Fermi. This is for Fermi people. This is clearly a signal that is above threshold. This is something true, and so we have this coincidence. Here it's a little bit explained. There are two detectors of different energies, and you see this delay of 1.7 seconds. So the probability of a random time and position coincidence, because there is also some pointing available in this event, is 1 against 20 millions. And so it's pretty clear that this is coming from a common source. And so we have a strong indication. We have one case in which short gamma ray bursts, which are an enigma in astrophysics, are generated by binary neutron star coalescences. Maybe not all of them, but certainly some of them. So what does this mean? First of all, as a fundamental physics, well, gravitational and electromagnetic wave arrive 1.7 seconds apart after about, this is something like 100 million years. So this means that they have the same propagation speed within one part out of 10 to the 15. So again, we are in the situation that it is not the waves that decide how they travel, but it is a curvature of space-time that says how they must move. And to take the word of John Archibald Wheeler, we say matter tells space-time how to curve, and space-time tells matter how to move. This is the summary of what we saw at the beginning. But we can certainly say that matter and waves, because waves carry energy, tell space-time how to curve, and the space-time tells matter and waves how to move. And you see, you have the two signals that travel, one beside the other. They can cross, they can meet dark matter, whatever, we don't know. They enter a galaxy and they arrive at the same time. So this is the first extraordinary verification of the universality of free fall, the free fall for waves that are traveling. This event, with Virgo entering in the game, could be localized with an extremely high precision for our standards. Before, with two detectors, you would have circles, more circles, all covering the full sky to give the position of the event. With three detectors, you are able to triangulate, and you are making some small, you are finding some small spot in the sky. So it's about 30 degrees squared, so 6 by 6 degrees. And you can also have some indication of how far you are. And these are reconstruction of the distance of the event, because from the amplitude of the wave, you get an idea of what the distance is. And so you can block the volume in the universe where the event occurred. And in this volume, there is a host galaxy. There is a galaxy, MGC 4993. There are other objects. There were other objects there, but people were rather clever. People were warned of this. We had set up a warning system. And after about 11 hours, when sun was setting in Chile, the SWAP telescope was looking for the sky in that region, comparing current images with catalog images. They were ready to do this. This was prepared, and they found a new star. The new star is here. So this is the old image, and this is the star. Okay. So already this is something really a new way of seeing things. Usually, new stars are seen by chance. People look at it and they compare it, and perhaps it's there, perhaps it's not. Here, something was able to point the telescope to where the new star would appear. Now, this is a faint star called the kilonova, compared to supernova. And it's very important that we have a fast warning, because this is not a real star. In fact, this is something that is cooling down. The star is blue here on the 17th, and 4 days later, it's red. It means that it's the object is cooling down, and it continues to emit radio waves for a long time, but disappears from the optical spectrum. So to catch these events, it is extremely important to have this early warning, and we have demonstrated that gravitational wave can give this warning. This event has a particular meaning also for astrophysics, cosmology, and for us. Let me recall what is going on. So we understood that this event was made out of two neutron stars. Now, we know that the sun is burning primordial hydrogen that is coming from the Big Bang, and this is the reaction that occurs. At some moment, there is some energy that comes out, and this is what makes the sun shine. And because the sum of the masses of the four hydrogen atoms is higher than the sum of than the mass of the helium, and so some energy has been emitted, given by the difference of the masses. Then other reactions in the following times of life of a star, not only the sun or other stars, are able to do something more complicated and produce nuclei that are an increasing atomic mass. And this goes on until you reach iron. Iron is the most stable nuclear nucleus, most stable nucleus, and so it's not possible to produce in this way other elements, at least not with the energies present in the star. Now, what happens in this environment where two neutron stars collide? You have a concentration, density is extremely high, and you have a concentration of neutrons that can pile up one above the other. There are also protons around, and they can build whatever nucleus you can imagine. And this is a chart in which you have the neutron number here, and you have the proton number here. So here it's going to go up to 92 or something like that, where there is uranium. And the stable elements are in this island of stability. There are some very specific combinations of protons and neutrons that make stable elements. So this is a simulation that says, okay, let me pick up an initial condition in which I have many combinations of proton and neutrons, but essentially with the same number of proton and neutrons on this diagonal, and I let them evolve in this system where the two neutron stars are colliding. And in this graph, you have the mass number. Remember that these are going to be medium weight elements. These are going to be high weight elements. And so at the beginning, you produce these elements. And while the simulation, and so the real process, because in this case we are presenting the real process, goes on. Sorry. I'll let the movie go until the end. See that we are generating whatever nucleus you want. And then at the end, these nuclei are going to decay, they emit energy, and you will remain with only the stable nuclei. But the point here is that this process is able to produce all elements that are higher, that are more heavier than iron. And so this is a process that is able to produce gold, lead, uranium. It allows to create the very heavy elements, something that we didn't know how to do with say the supernova mechanism, with other mechanisms in with the stars. So this event appears to explain the abundances of all the elements, and in particular I pointed out platinum, gold, and uranium, as we can see them in our galaxy. So the amount of events of that kind that are rather rare that occur are able to justify the fact that we have some gold on Earth. So this has been possible because the interferometers are almost omnidirectional. They are sensitive above and below the horizon. The event can be on the other side of the Earth. Gravitational waves cross the Earth without being perturbed. You don't need to point them, and they listen. So there are ears that permanently listen to violent mass motion, and this motion usually anticipates electromagnetic emission. So this is true for this system, can be true for supernova explosions. And when the source direction is well constructed, this is, as we have seen, an ideal assist for telescopes. Telescopes need to be pointed. They need time to move, they need to program their pointing, they need also to be in the dark, but gravitational wave detectors, they work also in the daylight, of course, and they can produce these signals that can then be used by the rest of the observatories. And this was clearly the start of a new astronomy that really is using gravitational waves, but then is doing multi-messenger astronomy, because you look at gamma rays, at photons, ultraviolet light, radio waves, neutrinos, and to understand what has been going on in what has been a dramatic event in space. Now, we've been studying we are studying then black holes. This was one event on stars. We had many events with black holes, and then we can start really studying general relativity in strong field conditions, really in extreme conditions, something that cannot be achieved neither on Earth nor in the solar system. So general relativity is something that keeps very complex equations, complex in the sense that they are very difficult to solve. Nevertheless, they have been verified in a static condition in the solar system. There are famous measurements like the Mercury perihelion precession, even the Taylor-Hurst Pisa system has a periastron precession, and so this is verified by this complies with general relativity. And then there were solutions, for instance, the Schwarzschild solution for geometry and the Kerr solution, which represents a static and a rotating black hole, respectively. These were mathematical solutions. Well, this solution can be cross-checked with the data from gravitational waves. We can look at tightly bound systems, and we can look at the way gravitational radiation is generated. And by the way, we must check that gravitational waves indeed move at the speed of light, and that they have two polarization. So there are many things that we can start to do. Here I just put as a reference, there are a few papers that have been out. They can be found on the web directly, and they contain a catalog. So a list of what we observed in the first part of the third observing run. We observed some strange events which has an asymmetry in mass. And we really made tests of general relativity, quantitative tests. And there is work in progress. We are searching for signals that we have not yet seen, periodic signals, supernova signals, and stochastic background. Here I show is over the duration of this observing run 3, so this which was interrupted by COVID for 11 months, and here we've put the number of detections and the number of alerts. So there are either real detections that we confirmed rapidly because they were extremely clear, but there are also alerts that we send to to the observatories, to the astronomers, over which we said, okay, this could be a good event, maybe it's not. But these are the alerts that have been sent but not retracted. So there's quite some likelihood that that a good fair fraction of these are good events. And you see that we are above 50 such events. So this makes one event per week. We have been waiting for 100 years for this. In this pie chart, we can see the time. Okay, the colors represent, especially the yellow one, represents the time during which the three detectors were working together. And this is something not so obvious. These detectors are complicated, and they don't work. They don't like to work. They clearly need to be tuned, and they need maintenance. But nevertheless, we had the three of them together for about half of the time. So for about half of the time, we had the possibility to make the sky localization. And this is a good achievement, and we want to improve for the future. Some results. The one thing that we know is that the result of the merging is a rotating black hole, and general relativity is able to predict the mass and the spin, knowing what the two black holes, initial black holes were, and how they were moving. And here, this is a graph that represents the mass, the deviation from of the mass from the predicted value, the deviation of the spin from the predicted value, and clearly the zero deviation in both the mass and the spin from the prediction, a self-consistent prediction, because it is the same event that you're using to predict the mass of the final black hole. You see that when you accumulate several events, everything is accumulating to zero, showing that indeed general relativity predicts correctly what it has to predict. Okay, you can, just for the folklore, for just as a flash of what we are doing, there are a number of parameters that describe the waveform. And here, again, we plot the deviation of such parameters from the nominal value, which is the red line, which is the deviation should be zero. And you see that all the parameters that are considered are accumulating, are pointing to zero deviation. And this arrow here shows that by the time you increase the number of events, then the error, this is how much it fluctuates, the error goes down, so it improves the precision of the test of general relativity. And so this is an impressive agreement between the waveform and general relativity prediction. We have the propagation of the speed of light. This is foreseen by general relativity, but there could be a particle that is massive, and then the wave would travel slower. We have within these errors, we have already some indication it's not the case. But what could happen is that there is a dependence of the speed of the frequency of the gravitational wave. So low frequency wave that should arrive before could be seen later, and this allows to put some again limits on errors from general relativity. So again, we have these violin graphs that show you that you are near the correct, that you are in agreement with general relativity. The black hole is a bell made out of pure space-time, and it rings and it sounds, and its sound is a gravitational wave. So you have to imagine something that is space-time, that's all, but just so curved that it contains a lot of energy and it makes a black hole. And if you perturb it, it's going to sound. And by resonating, it will lose energy, and then it will go back quiet. So there is, as in the bell, you will have some frequencies, some decay time of several modes of overtones, and they are predicted by general relativity. And here we are beginning to see the overtones of the black hole, and we can make some prediction comparing the overtones labeled this way, 220 and 230. And again, the deviation from the prediction of general relativity is measured on this axis, and this is the point 0, 0, and you see that these events indicate that everything is working at this level of precision. Let me mention that the Nobel Prize of this year has been awarded for black hole to Sir Roger Penrose, Rainer Genzel, and Bill Gates. So it's an interesting system. As a conclusion, the analysis of 1/3 of the O3 events shows nothing unexpected. General relativity fits well gravitational wave observation. But these analyses were mostly standard ones, and now we are digging deeper and deeper into noise, and we are also improving the detectors. In fact, we will start in 2022 in the summer, COVID allowing. We like to publish this stellar graveyard, which represents all the events that we have detected. Every event is made out of 2 black holes that will merge into a higher mass one. And so we have many of them. It was a surprise that these events were at such high mass with respect to what was seen. It was a surprise to find black holes in some region which was not allowed by the stellar evolution. So there are things that we are learning. The little bit of time that I have, I will dedicate it to the future. So the near-term future is, you see, 01, 02, 03, 04, 05. We are planning to improve our detectors. This figure here represents the horizon, how far you can detect neutron stars. And so you go to 200 megaparsec, then we would like to reach 300, 200 megaparsec, which makes a lot of events, certainly more than one event per week. You can make one event per day. And we have also joining by a Japanese interferometer, which is now, which has been also running a little bit during O3. And we expect to have an interferometer in India, to be set up around 2025, 2026. It will be a third LIGO interferometer. And out of this, so 2, 3, 4, 5 interferometers with precise measurements of position, but also of characteristics of the gravitational wave can be made. Future in the little bit longer times is the Einstein telescope. And this is something, this is an artist's view. So we said that we need to go underground to cancel gravity fluctuations. You need to have long arms. You can build a triangular object, and so there are serious plans, and indeed there's a design for this that is being set up. Why we do this? Well, there are anyway much more sources out there, many coalescing binaries. We need to measure rotating neutron star, maybe find pulsar starquake, and supernovae, and the stochastic gravitational background. Maybe it's inaccessible. We don't know if it's not the standard one that might be accessible in some way. The Einstein telescope sees something is a triangle with sides of 10 kilometers and with interferometers that work at 60 degrees, the arm one from the other. And so this is a construction that allows number of tricks. You can resolve a number of questions about the polarization of the wave. You can build your you can detect your gravitational waves in a different way. What we expect to be the third generation Einstein telescope is the third generation interferometer network in 2035 is depicted here. And I will mention that there is a similar project of a cosmic explorer. This is something, this is a traditional, quotes, 90 degrees interferometers with 40-kilometer arms. And here is a small interferometer that will be dedicated to high frequency, but which has the particularity to be in the southern hemisphere, and so would help localization also there. So these are the plans for 15 years from now. To go back to the sensitivity curve, the noise curve, this is the experimental curve that we have now, and all these curves show what we want to do in 15 years. So it means gaining more than 1 order of magnitude in noise, extending at low frequency, and extending also at high frequency in order to make a very good use of these large infrastructures that are going to be built. This depicts, this slide here depicts what are the goals of these interferometers. So you are here, this is the center, the tip of the light cone. And if you go back in time, which means that you go away in distance, then you will go at higher redshift, and you will encounter the zone where the stars are forming. And if you are able to go further away, you will be able to listen to the universe when there were no stars around, because the universe was too young. So this is extremely interesting, because if you find a black hole here, this means that this black hole is coming from the Big Bang, or from the very early evolution of the universe. And so this would be something completely unexpected. There are theorists that claim that there should be, so we have to see. And so this third generation detectors, you see, so these are the extreme second generation detectors. There is a Cosmic Explorer 1 and 2, Einstein telescope here. They will go well beyond the time the stars have been forming. Okay. Now, the last thing that I will say, and I'm through, is that you can also use really free-falling masses to track geodesics in space-time. This is what you want to do to detect gravitational waves. And planets, not planes, and spacecrafts and perpetual free fall. So you can use them to measure the curvature changes from the separation between two satellites. So a laser interferometer space antenna called LISA has been designed, and has seen a lot of progress. There's been a mission, LISA Pathfinder, which has been extremely successful. And this is a triangular constellation of spacecrafts, 2.5 million kilometers apart, orbiting around the sun. You can detect waves that are oscillating more slowly, but this means that you are seeing events that are black holes that are heavier, so periods of tens up to thousands of seconds. So this is it's a picture of what happens. You see that you want to place 3 satellites here in a triangular formation. They won't stay like that if you don't let them go around the sun, and they will make this dance here. And this triangle will be 2.5 kilometers long, and it will lag 3 weeks behind the Earth, following the same orbit. This requires an incredible technology there. You need to protect the mass that is in free fall from the solar wind. And so the satellite is acting as a shield that follows the mass inside and uses microthrusters to maintain exactly the same distance from the mass which is inside the satellite itself. And then the light will be bounced onto this mass and the measurement will be made. There are many things that can be done with laser. It would be worth a conference, not by me because I'm not an expert, but just one thing I would like to mention is that you can use, this is a representation of curved space-time nearby a very massive, black hole here, and you would probe this space-time using small, quote-unquote, black hole that is going around and will, by its motion, is going to probe what is the structure of the space-time there. You will be able to see more massive and more remote black hole events, and you will be able to also there to try to understand the history of black hole formation. So this is planned to fly in 2034. There were people still trying to fly earlier. In the late 30s, we might be in the situation in which we have all the ground experiments plus LISA and LISA. And so LISA could observe an spiral at its early stage, low frequency, announce to the ground, look, this day at this time, this direction, you will get this event. And so it's going to be, and this might be months or years later. So this is going to be extremely interesting because it will allow to test general relativity in extreme detail and precision. I'll finish.
Francesco? Huh.
I think, David, I think we've lost Francesco just then.
Yep. Well, just at the point we were going to grill him. Shall we see if he can reconnect?
Yeah, I'm sure he'll be aware.
Mm. Yes, he's in the waiting room, so
Oh,
Bill,
okay.
can you admit him?
Yep.
Okay. So Francesco, welcome back. Can you share your, do you want to share your screen again? We've got lots of questions for you.
He's muted.
You're muted.
Can you hear me now? Yes.
Perfect.
Yes, good. So let me just be okay. Clearly we have some problems. Let me see what I can do.
Okay.
Yeah,
we're seeing the screen we were seeing before, so.
Good. Okay, that's already something. Right. And so yeah, we are lucky because in fact this was the end, because an uncharted territory is in front of us, and so we must be prepared. And so let me thank you for your attention. So we were at the end.
Okay.
I'm very sorry about it. Yeah.
No, that was a very dramatic exit. Okay. Right. If I can now perhaps ask you a few questions.
Yes, please.
There have been a variety that have occurred.
Oh.
In fact, I think you answered some of the earliest questions. The directionality, for instance.
Good. Mm-hmm.
Clearly, we want this to be part of astronomy, just like when radio waves were discovered from the cosmos. Radio astronomy has really changed the universe, our view of the universe. But there is a question that has been asked, which is, how do you communicate fast enough? You get a little chirrup that lasts for a matter of seconds, and how do you then communicate with the astronomical world to point their telescopes, gamma ray detectors, to seek whatever it is you've heard?
Yes, thank you for the question. It's in fact, we are using a system that has been set up by astronomers, a system of alerts, which is rather simple. The real problem is to make the computation so that we are able to give the information, and we are working on this. And so now the latency is could be a few minutes. But there are ideas, as we didn't have time to go into the details, but you've seen that the two neutron stars are orbiting, are seeing Earth orbiting for 1 minute. And so computing from the early phase of the orbit might allow to give the signal even before the end of the coalescence. So this is a fascinating goal that we are trying to pursue, and otherwise we need some time. Sometimes the detector is noisy. We want to be sure that it is not a false alarm. So it takes a little bit of time, but clearly we want to reduce as much as possible the time. And when the event allows, we would like really to even to anticipate, but this is half a dream, half reality.
Another question, rather similar, the significance of the time difference between the receipt of the gravitational waves and the gamma rays. What information does that convey?
This part is model dependent in the sense that it's not completely clear at what time you have the gamma ray bursts. You really need to model this neutron star coalescence and this emission of radiation. And in fact, the papers were mentioning something like even hundreds of seconds of difference between the two events, because before you have the coalescence, then you have the ejection of all the neutrons, and when you have the various collisions, the matter is heating up. Then at that time you will have gamma ray bursts. So there is at the source there is some uncertainty in time.
Right, thank you. I have a question. Italy is seismically active, and yes. I noticed that you took precautions to make sure you could measure during microseismic activity. What if you've got a macro seismic event, earthquake? I mean, it's does the whole system shut down, or you must have surely thought about it?
Yeah, there are different degrees. In fact, some strong seism around the world, when they arrive and where they are announced in advance, we are monitoring, say, the U.S. Geological Survey and our own seismic institution. And we place the interferometer in a somewhat more protected mode, in which you are able to make a stronger force on the mirrors. Because the problem is that you must be so tiny in introducing noise that the maximum force that you can apply is limited. You have a dynamic range. It's really a problem of dynamic range. And so you try to put yourself in a position you can manage stronger oscillations, but sometimes you just hit the dynamic range, and then the system, which is a complex feedback system, unlocks. And
Yes,
the point there is that we are able to relock in 5 minutes if the masses don't move too much afterwards.
okay, that's fascinating. There is another question from Stephen King. In fact, what are the merger mass limits of the current observatories, gravitational wave observatories? So how big is it?
Yep.
Mentioned solar masses. Perhaps that's the units you could use. I don't know.
Should have a graph somewhere. Oh, I think I suppressed it. Just let me pick it up. I'm trying to be short. I've been cutting a number of things. Okay, no, I don't have it now. Okay, so the current detectors, they can detect something like 100 solar masses on the upper side, and then the lowest on the lower side, it depends on where the event is, because if the event is nearby or in the galaxy, it could even be a small mass that can be detected. But otherwise, as you've seen, we have been able to detect 1.4 solar masses, which are the neutron stars, at a distance of 40 megaparsecs. So it's really a game of the distance. And one thing that it's worth mentioning is that with distance, by increasing distance, you increase the volume that you can listen to. And so the rate of a source of events can increase with the cube of horizon. So if you improve by a factor of 2, you get a factor of 8 in rate. And this is quite fascinating as a perspective. But then for the masses, it really depends on where we are. And there is some subtle trade-off in ET, so that you can you can detect even 10,000 solar masses, but not too far away.
Okay. We're going to have to wrap up very soon, but can I ask you a sort of personal question? When you were working towards a gravitational wave detector, which must have been a large part of your career, how many did you expect to detect? Are you seeing any more than you expected, or many less?
In fact, the rate for coalescing binaries was not so wrong, but the real surprise is, and this was a surprise for almost everyone, is that we saw, and we are continuing to see, black holes first.
Okay.
Not only, and black holes that are much heavier than the ones that one would expect. In fact, the detection of heavy mass black holes sometimes is tricky, because you have waveforms, and these waveforms, they are the model of a system that you have chosen. And if you don't have chosen the right mass, if your mass, the mass of your models is too low, you are not going to detect the event.
Okay.
And so you must, you must be careful in really foreseeing the unexpected there. And so black holes are the real surprise there.
Okay, thank you. I seem to remember, you know, I was involved in, of course, LISA Pathfinder and the LISA planning myself. And I always consoled myself while working when nobody'd seen a gravitational wave by something called the millisecond pulsar, which was a pulsar that was slowing down. It seems very different from what we've heard about today, but where does that fit? That was probably about more than 40 years ago, the discovery of that, 50 years ago, I would think. Where does that fit into the picture? Because it always consoled me that these gravitational waves had to be there. So it was worth, you know, if we could detect them, they would come to visit us. Do you have any comment about that?
Yes, this time I can show the gravitational wave spectrum. And on the right, you have pulsars. And the millisecond pulsar would be at the very end of the violet band at 10 to the 3 at 1 kilohertz. There, the tantalizing thing is that, first of all, we know of 2000 pulsar, but there are 1 billion neutron stars in the galaxy, and so there are many that you might see only by gravitational waves. And this millisecond pulsar, as far as we know, we obtain them because there is accretion, and they're extremely stable because there is some mechanism of accretion. And unfortunately, this mechanism of accretion is going to polish the surface of the star in such a way that your quadrupole moment, the asymmetry that is needed for gravitational wave emission, is going to be wiped out.
Oh, okay, well,
but nevertheless, we are continuing searching, yes.
Okay, I think we better wrap up the questioning at this point, and I'd like to turn over to my predecessor as president of this society, Roderick Rhys-Jones. Rod, the floor is yours.
Thank you, David. Can you hear me?
Yes, we can hear you.
Lovely.
Fine.
Well, it's terrific to have Professor Fidecaro in spirit in Imperial College, if not physically. It's some considerable time that I've known him. I met him indirectly through Professor Luisa Schiffarelli, who gave a talk at Imperial College, organized, I think, by the Italian Society in 2014. She had just stepped down as Minister of Education. She was also president of the Italian Physical Society. And I spoke to her afterwards and told her that I was interested in science in Tuscany, lots of other things about Tuscany too, and both ancient and modern. And I'd always wanted to go to the Leaning Tower of Pisa and take John Burland, the imperial professor that stabilized it. And she immediately said, she said, we're having the centenary of the congresses of the Italian Physical Society, and she asked me to attend. My Italian wasn't quite up to it, but what fascinated me about all the talks and lectures were that all the slides were at least in English. And I was told by the many academics that were there that internationally the slides were presented in English, but seeing as they're all on home territory, they were all going to talk in Italian. And that's where I met Francesco Fidecaro at a visit to the Gravitational Observatory. And we got together and he invited us, friends of Imperial College, across to see it. And we've had 2 trips there to see it, and he's been most welcoming. And we've also visited Pisa University and Florence University. And the Italians are always been most welcome and welcoming. And I look forward to perhaps organizing another visit when we're not locked down. And I'd just like to say what a fantastic tradition of physics that Italy has. David mentioned Galileo and Fermi. And there are many women physicists too, not only Francesco's mother, but many others too. And I just think that we should congratulate you and be proud to have been able to entertain you this evening in England. I'm not sure where we are. Perhaps we're in hyperspace. Anyway, I'd like to thank also Azad Ayub, who gives financial support to Friends of Imperial College. He met Professor Fidecaro on the second visit that we made to Italy. And just like to say to, I've just got a slide here. Just like to say that we have some new events coming up. Next Wednesday, we've got an exclusive discussion with the head of Department of the Earth Science and Engineering on their involvement with the Mars 2020 mission. And on the 4th of February, we've got Sir Peter Knight talking about the second quantum revolution. He was attending this lecture this evening, I noticed. And so you're all very welcome to that event. And lastly, let me say that we have members are gathering together as we do at the lecture theatre in Imperial College. Afterwards, we have drinks down below. We have a members event now at 8:30. If you didn't get the email, please send an email to Angie and she'll send it out to you. And if you felt you enjoyed this so much, you'd like to give a donation, please go onto our website. It would be very welcome. But now perhaps we should, before we go, we should stopping the videos. Let's and also unmute ourselves and give a round of applause for Francesco Fidecaro for a fascinating lecture. Thank you very much.